Hello students, welcome back to the next topic on biasing and stabilization. Myself Gunjan Mittal Roy in the Department of Electronics and Communication in Jamtech Greater Noida. So in the previous topic of biasing methods, we have covered fixed bias and collector to base biasing network. And in this video, I'll be considering the third method of biasing, which is potential divider along with bias compensation techniques. So the third and the most popularly used method of biasing and stabilization is potential divider or voltage divider method. It is also called self-bias or emitter bias circuit. It has a difference with respect to the fixed bias method, that in fixed bias there was a resistor connected at the base only, whereas in potential divider method potential divider network or a resistance network where the two resistors are connected in series is connected between collector and base, and a resistor at the emitter is also connected, which forms self-biasing network, and therefore it is called as self-bias. So the potential divider network consists of the two resistors R1 and R2, and the self-bias resistor is Re. Now we have to determine the values of IE, VBE, IB and VCE. Most of the time VBE is considered as 0.7 volt for a silicon diode. So we have to mainly focus on IB, IE, IC and VCE. And with the help of these values we will be deriving the S factor, stability factor. So the first work to do the further processing or mathematical analysis is to convert this resistance network in this form, which is shown here, and where RB is the resistance of R1 and R2 when taken in parallel. So VB is the voltage between base and ground, so VB is equal to VBE plus VE, where VE is IE into RE, and VB is the voltage across the base resistor RB. So if we consider it I into RB, then VB equal to VBE plus IE RE. From here we will derive the value of IE. From in this particular network we will not be deriving the value of IB from the KVL at input port, as we were doing it in the previous networks of fixed bias and collector to base bias. In this method we will be focusing on determining the value of IE from the input port. Now we have to determine the value of VCE, so for that we will be applying KVL at output port, and we know that KVL is VCC equal to ICRC plus VCE plus IE RE. I hope all of you know how to apply KVL and KCL, and this you must have covered in first semester network theory and second semester electronic devices. So we will arrange this second equation in this form, that VCE equal to VCC minus ICRC minus IE RE. After that we will be redrawing the circuit, and where we will be using Thevenin theorem, and in that VCC and R1 are taken as the source resistance and source voltages, and R2 is the resistance at the base. So they two come in parallel. So therefore, to determine the Thevenin equivalent resistance, which is taken from the right hand side of the device, this arrow is showing the direction from where the Thevenin equivalent resistance is applied, calculated. So RTH, Thevenin resistance, is given as R1 into R2 upon R1 plus R2, where R1 and R2 are both in parallel. So now we will find the value of Thevenin voltage Vt. Vt is the voltage taken across the Thevenin resistance terminal. The resistance terminal from where the Thevenin resistance was derived, the Vt is also the voltage of that particular terminal. So Vt equal to Vcc into R2, and it uses basically a voltage division rule. So voltage, whatever voltage we are determining across a resistor, so that particular resistor upon total resistor into the applied voltage. This is the formula to derive the Vt. So Vt equal to R2 upon R1 plus R2 into Vcc. So this is mentioned here that we have used voltage divisor rule. Now after that we will come to this circuit where Rb will be giving a Thevenin resistance and Vt is the Thevenin voltage, and after that the circuit is same as it is. So the circuit outside the arrow, in the right hand side of this arrow, let me show you. This is the arrow, and from this the output side of this arrow will remain same, where the left hand side of the arrow has been converted into Thevenin equivalent circuit, where the circuit consists of a Thevenin voltage source and Thevenin resistor that are connected in series. So this is the now simplified circuit of potential divider network, and now we can easily apply the KVL at input port, and from here we will derive that Vt equal to IBRB plus VBE plus IERE. Now IE, we know that IE equal to IB plus IC, so we will put the value of IE as IB plus IC. Then we will solve this equation and get an equation in the form of IB. So equation 6 shows the value of IB, which comes out to be Vt minus VBE minus ICRE upon IB plus RB plus RE. Since we have derived the value of IB, we have a relation of IC, that IC equal to beta IB plus 1 plus beta ICBO. So if we have the value of IC and IB, so simply we can find IB as in terms of IC, which is IC minus 1 plus beta ICBO upon beta. Now we will differentiate this equation 7 with respect to IC, and if we differentiate it, we get del IB upon del IC equal to minus RE upon RB plus RE. So if we put this value of del IB upon del IC into the generalized equation of stability factor, which is 1 plus beta upon 1 minus beta into del IB upon del IC, so we are putting the value of del IB upon del IC as minus RE upon RB plus RE, and if we put it and solve it, we get S equal to 1 plus beta into RB plus RE upon RB plus RE plus beta RE. So this is the final S factor of this particular method. So from this S factor, we can conclude that the beta factor comes in denominator and it gets cancelled out. So relatively the value of S is closely 1 or very small. So therefore this brings us the best stabilization or best stability of the Q point. There is one more technique to to maintain the Q point at the middle of the load line, and that is called as the bias compensation. So bias compensation is a technique which is used to stabilize or maintain the Q point at its original position. And this technique uses temperature sensitive devices such as diodes, transistors, thermistors and sensistors. So here few methods are shown as per the syllabus. So first method is showing you the thermistor compensation technique. In the thermistor compensation technique, thermistor is a device which is connected in that circuit. It is called as thermal resistor. So this particular material is made up of a semiconductor and which has the property of negative temperature coefficient of resistance. That means as the temperature increases, the resistance decreases. The slope is also showing you that as the temperature is increasing in x direction, the resistance is decreasing from y-axis to x-axis closely. So the temperature coefficient of resistance is given by del RT upon del T, and it is NTC in case of thermistors. Now this is the circuit which is using thermistor, and this is used in potential divider method. So in place of resistance RB, it is written over here that in place of resistance RB, thermistor RT is connected here. Now what will happen if the temperature increases? So when the temperature increases, the resistance decreases because of the property of the thermistor. Due to that, VB decreases, which brings out decrement in VBE and therefore decrement in IB. And since IC equal to beta times IB, and if IB decreases, IC also decreases. So with the increase in temperature, IC decreases, and if IC decreases, the change in IC decreases rather, then change in IC is less with respect to the change in temperature or change in leakage current. So it brings us the stabilized Q or stabilized operating point. So this gives us compensated Q point. Next method is by connecting the thermistor between collector and emitter as shown in this circuit. And here also, as the temperature increases, resistance decreases because of the property of thermistor. Now due to this, emitter current IE decreases, which results in increment in VE, and that VE brings the decrement in VBE, decrement in IB, and decrement in IC, because IC is beta times IB. So these things are interrelated to each other, and therefore the stabilization of the Q point or compensation is done. Sensistors is the another approach of using compensation, where the sensistors have a positive temperature coefficient of resistance. That means as the temperature increases, the resistance also increases. So change in RT with respect to change in time temperature is positive. So delta RT upon delta T is positive. So it has PTC, positive temperature coefficient of resistance. Now the use of this sensistor is in this circuit as shown here. In this again potential divider network is used, and RT, which is the sensistor now, is connected in place of resistance R1. Now we have to see what will be the conditions to compensate the change in collector current. So here is the cycle, which says as the temperature increases, resistance also increases, which decreases the emitter current, decreases the base current, and decreases the collector current, and therefore the compensation is achieved. Next compensation technique is diode compensation technique. Here a diode is connected in the emitter arm after the emitter resistor as shown in the circuit, and the bias battery is also connected across the diode as shown here. Now what condition occurs if the temperature increases? When the temperature increases, since diode is a temperature sensitive device, its VBE also increases, and if VBE increases, the variation in VBE is 2.5 millivolt per degree Celsius. So as there is a rise in 1 degree Celsius, the change in VBE is 2.5 millivolt. The variation of VBE is cancelled due to reverse polarity, but the diode is having a reverse polarity here. The battery is connected in reverse direction, so the diode has a reverse polarity. Due to this, the variation in VBE is cancelled. So VBE equal to V plus IBRB plus VE plus VD, and therefore whatever is the increment in the temperature, VBE is compensated. The change is compensated. Here is another circuit of diode compensation, and which is also working in the same way, but it having a resistor diode in the potential divider network as shown here. So this brings another compensation technique. So with that, I would like to conclude the biasing network and the compensation technique. In the biasing, we have done 3 different types of biasings, which are fixed bias, collector to base bias, and potential divider. For all these networks, we have determined the stability factor, and S is best for potential divider. Thank you so much.